Let's do something else. Okay. So hopefully you're able to visualize that without the animation, right? So you get the idea is this thing goes along, the pressure, is constant over a plane. That's the idea of a plane wave. We're going to talk more about this stuff. That'll make more sense. Okay. What other brilliant thing's going to do for you here? I don't know what that is. So now we're going to look at a second kind. That's a plane wave. That's a spatial sort of a wave. Planes moving along. They get from here to here. Maybe your ear is here. Right? Let's now look at type number 2, a spherical wave. So this will be a little bit different. It's not just like the plane wave. So it propagates in all directions from a point. All right, so the key words here are all directions from a point for a spherical wave. The key word for the plane wave that I underlined was along an axis. All right, so that one just goes along one axis. This goes everywhere. So the best example is like a light bulb, like that. This is what light bulbs used to look like. Here you go. There's a filament light bulb. So the way you would think about that is light goes this way and this way and this way in all directions, all radial directions, and the origin is here where the filament is. So they're often represented just by drawing circles like this, evenly spaced circles like that. They're very hard to draw in 2D. They're very hard to draw in 3D. Actually, a vector spherical wave is difficult. But what happens is you would say, well, okay, if I were going to plot it now in space, I'd say this is kind of like the maximum here, and maybe this is the minimum, and this is the maximum, and this is the minimum like that, where this is the radial direction. But of course, in spherical coordinates, anywhere from the origin is the radial direction. So you could also say it's going to look like this, and come down to there, and go up to there, and come down to there, and go like that. Radial direction. The same thing in every radial direction happens. Right? That's all it is. So let's look at our example is light. A light bulb, not quite a point source, but close enough. Now let's write down what the solution to the wave equation looks like. Right? We had string. You're good at that. We had plane wave, looks just like string. You just have to realize we're talking about a physical extent rather than a string. But now this one's going to look different. Light is an oscillation of the electric field. So that's why I'm writing E. We want to know what's the electric field everywhere in space. But since we're doing spherical, we just need R. We don't need X, Y, and Z. We just need R because we're assuming things are spherically symmetric. Right? All that matters is how far out you go. The angles going this way and that way don't matter. Okay? So it equals some amplitude, but that amplitude depends on R now. That's what's special about the spherical wave. One, it's spherical, and two, its amplitude is not constant. Okay? Sine, and the rest is basically the same, kr minus omega t plus phase, phi naught. Right? So the main interesting parts is that the amplitude decreases, you can see here, and that it along all r here, right? Kr, not just kx, not just ky, not just kz, but along all kr. Okay? Goes in all directions. Now,